are commonly lost in the small cell lung cancer, and the newer therapies such as antibody drug conjugate and also immune therapies are upcoming. All right, thank you so much. And if you have any questions, I will be happy to take it. Do you think there's subtypes of small cell lung cancer? Subtype. The heterogeneity of the... Yes, I think so. Yes. So actually, in the MEPI study, she actually tried to group a small cell lung cancer based on the microRNA expression, and that seems to be, and the expression of certain microRNA may correlate with sensitivity to a particular type of a drug. So that seems to be the case. Okay, well, we'll be going shortly for a tour. Come out in the hallway. All right. Thank you so much. Okay, we're going to get started. Dave Wink is going to be talking about biochemistry of redox species. He's coming down from Frederick, and he may have run into a little traffic on I-270. So we're going to start with Stefan. And Stefan is a senior investigator in the Laboratory of Human Carcinogenesis. He's head of the molecular epidemiology section. And you'll see from his accent that he was educated in Germany. And he got his PhD in 1992 from the University of Würzburg. Subsequently, he came to MCI, and he's been a tenure track investigator since 2001. He was tenured in 2010. The title of his talk, Contribution of Oxidative Stress to Human Cancer, Evidence from Cancer Epidemiology. Stefan. Okay, thank you so much for the introduction. Thank you for coming. So yeah, I will look at the relationship between oxidative stress and cancer development from a kind of a different angle, from a laboratory standpoint, or more what evidence do we get out when studying the population? And when we study the population, we usually cannot study the mechanism. So what we're going to do, we look at exposures and association with disease. And what I want to tell you, what kind of evidence do we have out of a population study that oxidative stress is very important in disease development. While we do not have mechanism, and you cannot really conclusively link exposure to a disease development out of epidemiology, you can always have a confounding kind of an observation. It's still very important to have evidence from epidemiology. When we do experiments with cell culture with animals, we may get beautiful results. We use something, show it on a cell, it transforms the cell gets more present. We do it with animals, we get the tumor of the old man. This is a really important compounding cause of cancer. And then usually after we typically those initial observations, epidemiologists get interested in and say, okay, let's study the population if we can. We cannot always. But sometimes we can very well. And they say, okay, how is it linked to the disease? There is no linkage. And this may have something to do with there is no linkage. Second, it may have something to do that in the population don't have the concentration. This was not achieved. So that is not an important link. And what it tries to do so much in the laboratory for human disease, that is just not so important. This could be disappointing for the research, but it's really important for society to know those kind of things. Because there's a limited amount of money, and we have the money we have to use. We have to make our decisions how we how we communicate with the population, and how we try to protect them. By protecting the population, we have to send otherwise it's where we get the best impact out of our money. Okay, good. So what is the evidence that oxidative stress is linked to cancer? I will go through a very little bit in introduction. Is here are the hallmarks of cancer as it was described by Hannah and Weinberg 10 years or more ago. They had these kind of hallmarks that is common to most cancers. And this kind of schematic was then modified several times. Here it was modified in 2009, and they added two hallmarks to it. And one hallmark that was added is now oxidative stress, saying that the production of reactive oxygen is usually having cancer. And one important mechanism what it does is that you get DNA damage. It can
be up in a precancerous lesion and it leads to cancer, or it can be up in cancer and it leads to cancer progression. So it's very important, and at least out of experimental systems. And then there's a question, how is it important in the population? What causes of oxidative stress in the population? And if there's an excessive production, how is it linked to disease? And how can we interfere or prevent? And here again, how do we get increased oxidative stress in a cell, in an organ? What are important factors? All factors are very important. Dietary factors that we believe are important. And then there's also disease metabolism. The metabolism, like diabetes, leads to changes where we get increased production of reactive oxygen species in mitochondria, or we activate an enzyme, the NADPH oxidase. Then we get these reactive oxygen species. They can cause damage as much as cell, cause damage DNA, protein, or lipids. But they can actually also work as signaling molecules, secondary messenger. And it's very nicely shown. This is the NF-κB using kinase. You get upregulation of NF-κB. There are other mechanisms that are also lead to upregulation that increase transcriptional activity of NF-κB. That's what you get. And NF-κB is really the classic transcription factor that mediates one of the oncogenic function of inflammation. And there's another pathway that actually leads then to a similar activation of AP1, another transcription factor. That's all from molecular studies. And we also know now, that NR2 is just the opposite kind of activates the cellular antioxidant response. Is another transcription factor to see how complex it is regulated. What's supposed to be a super suppressor, okay, you say oxidative stress is pro-tumorigenic. You have something that protects cells from oxidative stress. It should be a super suppressor. But it turns out, and I cannot go into details, it's true in many situations, but sometimes NF1 upregulation is oncogenic. It's possible to many times, many times the point that we think something works a certain way, and then when we have the data, it sometimes works the other way. What we also have in cancer is really the consistent downregulation of antioxidant enzymes, which shown here, and the oxidase, and then upregulation of oxidant enzymes like oxygenase 2 and antioxidant 2 tables when it comes to talk about this. So what we have is really, and what I said, hallmark of cancer, oxidant states common in cancer cells. Many cancers poorly metabolized hydrogen peroxide, which is on one side, can cause damage, but it's also really a signaling molecule. And this concentration of these metabolites are increased in cancer. This is actually old stuff. So that's kind of what that's the point why people, populations, and scientists have got an interest in studying oxidative stress in human population. So as I said, usually do molecular and cellular research and animal studies that we start out with. Then there's also nutritional research, and that's many times observations here then are followed up by observational studies, and then observational studies are positive. You may decide to put money into intervention trials. And it's most expensive kind of a study, but also most conclusive. And then this is here all the the relation between oxidative and cancer, and we can look at disease onset, how it influences disease onset. We can also ask how it does influence disease progression, and the effects of disease onset and progression will be related. And it's just opposite actually, in the Bible. So in epidemiology, what do you study? Yes, certainly the evidence from experimental research, a certain exposure, the function or signal to oxidative stress, so epidemiology looks at infection, chronic inflammation, environmental factors, occupational factors, assuming that signaling through oxidative stress, and then we look at now it's related to disease, and we are interested in cancer, how it's related to cancer. And then we also are interested in how diet is related to cancer. In part, some diets will increase oxidative stress, others actually will protect it, will decrease it, and then we want to see how these diets are actually related to disease, and then perhaps make recommendation to the public. So, and then, these are factors we want to say we can modify it with information, and if there's strong association, we start communicating with the public and tell them, from the lawmakers, how we can restrict certain exposure or how we can change behaviors in the population. But then that also has predisposition, the predisposition that's also easy to deal with. If we are lucky, we can develop therapies, but if there are evidence that oxidative damage can also be caused by inherited predisposition, then yes, there are some high-risk diseases like Wilson's disease and hereditary hemochromatosis, where we know that certain mutations can cause these diseases, and people who develop these diseases are predisposed to cancer. And in many ways, we just know that. And it gives us evidence that oxidative stress is really, let's deal with disease and copper overload disease and iron overload disease. Everything who's coming next time, we'll talk a little bit more about it. And many other conditions develop, and there are also good. Cancer is just one of them. It's very hard to deal with that we can prevent it, even we have that information. That's many times we can inherit diseases. We know how it works, but it's not so easy to treat it. And then there are low moderate risk factors, genetic risk factors. These are usually simple nucleotide polymorphisms. There are other modifications in our genome that takes everyone from you, and everyone who has the moon is different from the other person. Some of these genetic variants affect functions of genes, and can actually in extreme cases lead to a knockout of function. And people have studied these genetic variants and how these genetic variants relate to diseases like cancer. Then here's just one example, just a use defined continuum. Jeden study, when you study almost all known genetic variations at one time, you don't study all, but you need to use SNPs that are linked to many disease-related ones. And then the criteria also identify genetic susceptibility, low side of diseases, ulcerative colitis, and the AIDS. And they know that many of these variations affecting genes that regulate immunity and autoimmunity are related to ulcerative colitis. That means that you are very unlucky and you carry a certain number of those genetic traits that increase your risk of an increased risk of ulcerative colitis. But usually this kind of genetic variation, they confer only a low risk of the disease to an individual person. It's more on a population level. So these risks are common in the population, and may explain that we have 5,000 per year in the population develop a disease, and may explain 500 of those cases. And then we can now say that we have an explanation for 10% of the cancers why they develop in the population. We will not be able to use this information for anything. But at least we have an explanation for it. Okay. We started years ago one SNP that was in the MNSOE gene, manganese supported dismutase. That SNP is to an extraction of amino acid. Then you have the ALA, and the enzyme has the ALA amino acid. Then it's more located in the matrix of mitochondria. The valine is more located, it's more membrane bound, so it's a different location. And people think it affects the activity of it affects the way how MNSOE can detoxify isotops. And we found that breast cancer patients who had two alleles of the ALA, means all the MNSOE that is produced as an enzyme is carries ALA, they had actually poor survival, and the other ones that we couldn't use the therapy. We had the data indicated that they are not responding as well to a certain type of therapy than these ones here. It can be important information. You can use it then to develop a test, and when you give people patients that therapy, and people confirm that everything with it has to be confirmed, and they can confirm that, and there's really a big difference between those with one genotype with the other. Develop a test, and you determine first before you treat the patient what is their genotype, and then if they have a genotype that does not respond to therapy, you will not use the therapy. That's ideal. Okay, so let's go to cancer causes worldwide. What causes cancer? There are estimations that nutrition is associated with 30 to 35%. Second is tobacco exposure, chronic infection, high penetrance genes. Then you would look at mortality, cancer mortality. Tobacco would be number one because tobacco causes a lot of death examples. Nutrition is, you can say individual choices, best choice of a diet, but then it's not so easy. It's of course also a more traditional nutrition, diet choices for area that's not so easy to change. And here in the US or Europe, we have a Western style diet, but we think is a high risk diet when it comes to cancer risk. So that's not something you can really think also an individual choice. Okay, so how have we linked nutrition? How do we know that nutrition influences we can predict the cancer risk? It came actually out originally from migration, it was the most convincing evidence where actually people from low-risk cancer areas migrated into the United States and adopted the cancer risk of the United States within 10, 20 years after they moved out there and increased risk. And in the second generation, still also had to increase it and then continue. So you knew that kind of genetics is to create a different environment. Then we have the association studies, that is just the population, and you study exposure to extra risk. All studies you can use perspective studies, because it's much less expensive. But then ultimately you can use intervention sites. From all these, we got to categorize, when it relates to cancer, foods into two categories, where high intake of those foods lead to low risk of cancer, and these ones here, or high intake of these foods lead to high risk of cancer. And all of these, and I think it's really clear for those ones that have reduced risk, I would say that they are highly considered. Alright, so here it's just by looking at them, you would say, well, that's probably one of their functions. And that's also how people get interested and say, that's really, that oxidative stress becomes important in disease development, and we modulate it with our diet. And if we avoid the right diet, one thing we really change is we reduce oxidative stress. This is also why, like a vitamin industry came so into play, because you believe when you take certain vitamins, we reduce oxidative stress. And then it's good evidence from animal research. Here is for just one publication, Western style diet was fed to mice, and this is the Western style diet is shown here, and then they looked at the colon, and they found that there are changes in the colon depending on the diet. So this is just one example. These are lots of papers. And what the changes is when you have the Western style diet concentration of metastatic biochemical substances that indicate that there is inflammation of the liver stress, and then you have also these infiltration of macrophages, and therefore probably partly responsible for the oxidative stress. So yeah, there are clear changes that indicate diet increases oxidative stress. So then, so people did a lot of studies looking at diet in relation to cancer. I just summarize it here a little. I give you a brief background. So in the 70s and 80s, a lot of people did case control studies. And this was case control studies to look at cancer, and they reported, okay, there's a lot of food that's associated with cancer. And that was pretty clear that you eat veggies and you eat food, you have a decreased risk, and then certain other foods like different type of meats, or other foods that are really associated with an increased risk. Now this was, that's the time people used decided called case control. You give these questions to people who have developed the disease and people who have not developed the disease, and then you ask what's the frequency of an exposure in this population, and then you make association how that relates to it. That's one problem is that people who have developed the disease remember and exposure differently than controls. And that was probably a reason for this epidemic of data that people generated at that time. And then secondly, because the case control studies produced nice data, people said, okay, it's time to put money in better studies, and let's prospective studies. And in the whole population, maybe 100,000 people, and to follow them up for 10, 15, 20 years, because cancer is a rare disease. And in order to get enough cancer in your population, is a huge population still you have to follow it up over a long time. So that's not expensive, and then you have the power to analyze it. And then people started looking at perspective studies, many of these associations didn't come up no more. And they oh well, what did we do wrong? People worked at that questionnaire, and then even larger studies, yeah, no, people did not confirm most of the initial findings. So yeah, I think it's just something. It seems to be, this is some conclusions that seem to be just correct here. For the rest of cancer, I got the high intake of fat and processed yeast, decreased diet stable and healthy in the meta-analysis. So I think, yeah, well. The population gets obese and predisposes people to disease, maybe cardiovascular disease, but also cancer. I don't know when you look at the cancer side. And then actually turned out in the US population, it's not homogeneous because it's a population group, where African Americans are more affected by these, detrimental impact of diet in the United States and the European Americans. So here, these changes or increased obesity really gives them even a higher risk for these things and disease like cancer. And how does it work? What works in obesity? Because obesity has tested into systemic information. Here's how it works, what are signaling molecules that are more abundant in obesity. And again, we get to the same point, it activates NF-κB and APE1, and really, leads to a signaling, a pro-inflammatory signaling that is also pro-oncogenic. And we have systemic inflammation, it's just all over in our body. Here are the examples, liver, then here we have the muscle, then we have blood vessels, and then we have the pancreas. You have a systemic inflammation. You can actually measure it with markers in blood, so you measure inflammation marker blood, and compare obese versus overweight versus non-overweight to find the difference. So then, how does this relate to cancer? In 2004, this paper came out and gives us an estimate of how being overweight obese relates to cancer risk. And they made the point about 10 to 20% of all cancers in the United States are still obesity. So that was a pretty high estimate. It's now a little lower. So but it contributes to it. And here are just the cancers listed here from women and men. It's different in the relationship by gender. And, you can see as higher the relative risk is, as more associated is obesity or being overweight, is a risk to develop this type of cancer. So, lots of cancers are really, related to obesity. So you would say, this is something you can change, and you change your cancer risk, but that's not obesity. And here's a paper that came actually out of the NCI Division of Cancer Epidemiology in 2010 that looked at the risk of death from various causes, cancer, cardiovascular disease, and other. And then here, when you look at cancer, here's a BMI of 22.5 to 25 is a reference. And yes, as you have a higher BMI, your risk increases, so you have a relative risk of one. It would be, there's no increase from 0.05 to 5% risk increase, to 34% risk increase, 47. So the cancer risk increases with increasing age. So that has been confirmed as a question. Okay, so, and then there is a question that, how is that linked obesity to cancer? So one is that you obesity by itself causes chronic inflammation, but with overweight and obesity, you're also more likely to develop certain other metabolic diseases. Diseases like diabetes. People start getting interested in perhaps drugs that we use to treat these comorbidities can also be used in treating cancer. And one candidate that came out of it was metformin. That is a drug that decreases glucose secretion by the liver. It targets mitochondria, reduces oxidative production.